Newton's first law of motion, or N1L for short, and the concept of equilibrium. We're studying dynamics, in which we learned that forces, interactions, cause acceleration. But if interactions cause acceleration, then the opposite is also true. Newton recognized that if an object is not interacting with anything, or if all the interactions cancel out, then the object will not accelerate. Except it wasn't Newton who first realized this, it was Galileo, about 50 or 60 years earlier. Newton took this idea and rephrased it in terms of forces. So interactions are represented by forces, and every force has two properties. It has a strength or a magnitude. Some forces are stronger than others, and it also has a direction. And you'll recognize that if a force has a strength and a direction, then it is a vector. Forces indeed are vectors. So every force is either a push or a pull. Here, Newton is being pushed to the right by this person. Newton is interacting with this person. That interaction takes the form of this force to the right. Here, Newton is interacting with this person. That interaction takes the form of this force also to the right. These forces both are to the right. They have the same direction, but you see they have different magnitudes. This person is pushing harder than this person is pulling. And the lengths of the arrows there indicate the different magnitudes. Usually an object is experiencing multiple forces at once, so in that case we will need to find the net force, the sum of all the forces that are acting. This symbol here is the Greek letter sigma. You recognize this as the summation symbol. It means add them up. The sum of all the forces is what we call the net force. If there are three forces acting, you'd add up force 1, 2, and 3 to get the net force on an object. Let's look at some examples. So here's three examples of multiple interactions at once. Here, the first one, Newton is being pushed to the right and pulled to the right by these two other people. So he's interacting with these two people. These two forces here come in two different strengths, and we can add them up to get the net force. Force 1 from person 1 pushing, and force 2 from person 2 pulling, add to produce a greater overall net force to the right. So these forces are supporting one another, adding up. And that net force will, of course, cause Newton to accelerate to the right. These two forces in the next example are opposing one another, so they can partly cancel out. Force 2 is greater in magnitude than force 1. Person 2 is pulling harder than person 1 is. So here the net force, force 1, partly cancels out force 2, and the net force is still to the right. Newton will still accelerate to the right. Example 3. Here we've got two forces opposing each other but completely canceling out. Person 2 is pushing to the left, so there's the force from 2 pushing on Newton. Here's the force from person 1 pushing on Newton. They're exactly equal in magnitude, which I've indicated by putting a little hash mark on each one. That indicates that they're the same magnitude. So here the net force, here's force 1 plus force 2, is 0. They balance each other exactly. And that's a special state. That's what we call equilibrium. Newton here is in equilibrium because the two interactions it's experiencing are canceling out exactly. The net force is 0 in equilibrium, which of course then means that the acceleration is 0 in equilibrium. I guess at this point we can state Newton's first law more formally. In everyday language you would say, you've heard this before, an object at rest stays at rest, an object in motion remains in motion, but let's be more specific about it. An object at rest will remain at rest, we call that static equilibrium, or an object in motion will remain in motion with, this is important, constant velocity, we call that dynamic equilibrium, until your object interacts with other objects in a way that produces a non-zero net force. So what we're establishing here is kind of the natural state of an object. An object will naturally stay at rest, or it'll naturally keep moving if it was already moving. It'll keep moving with a constant velocity unless you interfere with it. Unless some interaction changes what it's doing, the object will naturally stay at rest or naturally keep moving with constant velocity. We call that natural state equilibrium. Here are the two kinds. And now that we're talking about equilibrium, the best place to do that is in outer space. Here we find ourselves in deep space. And that, of course, is where you'll look to see the constellations, the signs of the zodiac. Libra, in particular, that constellation represents the scales, and these sets of stars can be connected in this way to suggest that scale on the sky. The term equilibrium comes from this word Libra. Equal and scale. Equal on both sides of the scales, meaning a balanced scale. That's equilibrium. And in physics, equilibrium means a balance specifically of forces, a balance of forces. That's equilibrium. So if you're in deep space, far away from any other object, there's nothing to interact with, then you could just be drifting right on through. And if you're drifting in deep space, or just sitting in deep space with nothing to interact with, you're probably going to be in equilibrium. So here, static equilibrium, that could be Newton in his rocket ship, just sitting at rest in deep space, abandoned and forgotten, nothing else around. Not moving, no interactions, sitting at rest, static equilibrium. But you don't have to be interacting with nothing for static equilibrium. Another possibility is that Newton is in his rocket ship on the launch pad on Earth, just sitting there at rest. This is also static equilibrium, even though this time there are interactions. The rocket ship is interacting with the whole planet Earth because the Earth is pulling down on the rocket with a force of gravity. That's one interaction. The second interaction is between the rocket and the launch pad right here. The launch pad is pushing up on the rocket, supporting the rocket. So here we have two equal and opposite forces. Force of gravity from the interaction with the Earth pulling down, and the supporting force from the launch pad pushing up. And those two forces are balancing each other out, also creating an equilibrium. That force is zero. Newton is at rest. Dynamic equilibrium is also possible in space. Newton, in his rocket, could just be drifting along, not interacting with anything, in which case he would be moving at a constant velocity. So here comes Newton's rocket, just drifting at a constant velocity through the universe. No thrusters, no interactions. That's dynamic equilibrium. No forces acting on him at all. No forces, no net force. But you could have dynamic equilibrium with forces present as well. Let's say Newton turned on a couple of thrusters on his rocket. And suppose he had a strange rocket. Newton was a strange man. He might have had a strange rocket. Let's say his rocket had a thruster on either end. The one on the back exerting a force forward on the rocket, and also a thruster on the front for some reason, exerting a force backwards. So if he turns them both on at once, there's two interactions with these two thrusters, but they're exerting two forces that are equal and opposite. They're going to cancel. They're going to balance out. So in that case, if Newton turned on those two thrusters at once, they'd have no effect, and you would see Newton and his rocket still just drifting at a constant velocity through the universe with two thrusters not having any effect on him at all. That's also dynamic equilibrium. So, in summary here, an object is in equilibrium, equal forces, if the net force is zero, which means that the acceleration will also be zero. And then there are two cases, either static equilibrium, if you're at rest, not moving, or dynamic equilibrium, if you are moving, but at a constant velocity.